So we're about 1 minute past here, so we'll probably go ahead and get rolling. Thanks everyone for joining. For those of you that have not attended or I have not met before, my name is Joe Kenrick. So I work for Lunar Outpost, running the Australia branch over there. But today I'm representing the AIAA in our Space Resources Technical Committee. So myself and Jared Longfox are the co-chairs for the Space Resources Education and Outreach. And one of our initiatives has been this webinar series. So if you're new to it, we've been doing this for about a year now. We've had a lot of great guests. We kind of started with more government, higher level strategy. So we had some NASA folk kind of laying the foundations for us, and we've been transitioning into some industry talks now on those actually sort of executing on that vision. So if you're interested in watching all of these are recorded. This one will be, and it's posted on our YouTube page. So I think if you just search on YouTube AIAA Space Resources, this channel should come up and you can see all those previous talks. So to kick it off today, we got a great presentation by Erik Franks, the founder and CEO of Cislune Incorporated, giving his talk on pioneering the lunar frontier, Cislune's innovations in lunar surface construction and mining. So throughout the presentation, if you have questions, please enter them in the Q&A chat. It's a Zoom feature. You should see it on the bottom. Just enter them as you think of them, and then Erik will talk for about 30, and we'll have plenty of time. I'll read off the questions at the end for Erik to go through. So I'll pass it over to you now, Erik, to get us going.
Great. Yeah. Hi, I'm Erik Franks, founder of Cislune Inc., and I'm happy to be here today to speak to the AIAA Space Resources Group. Thanks for joining the webinar. Let's see. So a bit about me. I've founded 3 companies, including an online bookstore that shipped 1.6 million orders. Then I built a 4-passenger experimental Corvette engine-powered airplane, as you can see in the top left. And I went to International Space University Master's program in Strasbourg, France. And then I worked at Maston Space Systems in Mojave, California. You can see in the bottom left with the zombie rocket there. And that's when I met Dr. Phil Metzger for the first time. And they were working on vertical takeoff and landing rockets before SpaceX perfected them. Next, I applied to the Y Combinator startup accelerator that invested in my previous company, Tesseract, developing in-space hydrogen peroxide rockets for satellites. That company had 4 customer satellites that are in orbit right now using our propulsion tech, including Orbit Fab and the Department of Defense. As a quick aside, hydrogen peroxide is a very promising fully ISRU propellant that's room temperature storable, which can be directly synthesized from water when the sun is shining on the solar panels, and can release its chemical energy through a fuel cell to allow infrastructure to survive the lunar night. I then founded Cislune in 2021, located near Pasadena, in Los Angeles area, after talking with Dr. Phil Metzger some more, who's worked at NASA Kennedy Space Center and is now a research professor at the University of Central Florida. He's a world expert in lunar research and development, and we've been happy to work with him significantly. Cislune believes lunar propellant production can profitably refuel landers and then fuel satellites in Earth orbit. Cislune's mission is building the lunar fuel factory, and we're also working on enabling technologies in construction and mining. We've won 7 NASA SBIRs and STTRs, and also won round 1 and 2 of the 2023 NASA Entrepreneurs Challenge, pitching lunar propellant refueling. And we won the NASA Break the Ice Lunar Challenge Phase 2, Level 1, and we're runners-up in Level 2. The moon's surface area is vast, equivalent to the combined area of the United States, China, Canada, and Brazil combined. The 2015 U.S. Commercial Space Launch Competitiveness Act, alongside the 1967 Outer Space Treaty, create a unique legal environment for lunar resource commercialization, such as mining and settlement. Operators should develop the most strategically advantageous lunar sites at the peaks of eternal light, near a resource-dense, permanently shadowed crater. These sites offer continuous solar power, refueling for landers, compelling views, and direct data links to Earth. The Outer Space Treaty provides a protective framework that prevents interference from other parties, thereby securing a non-competitive, exclusive use advantage for first movers who utilize these locations continuously. This setup suggests a regulatory supported scenario where pioneering entities can operate resource extraction enterprises on the moon, leveraging the OST's principles to safeguard their operations against rival claims and disruptions. I believe human landing system launch pads that offer refueling and habitation may be the anchor commercial tenants that lunar settlements will grow around. As we look to the future, the commercialization of the moon holds enormous potential. It opens up possibilities for innovation, tech development, and economic growth on Earth and beyond. This isn't just about resource extraction or scientific discovery. It's about pioneering a new economic sphere that could have far-reaching implications for the way we live and work even here on Earth. 51 years have passed since humans last set foot on the moon. Now we stand at the beginning of a new era of lunar exploration, with advanced technologies such as SpaceX's Lunar Starship, boasting a remarkable payload capacity of what they hope is 200 tons reusable. We're on the brink of a revolution. In the last 51 years, our endeavors in Earth orbit have improved life on Earth through advancements in telecommunications, GPS, Earth observation. It's now time for the next giant leap, unlocking the moon's vast resources to make space more accessible and sustainable for everyone. Earth orbit launch costs are about $2,000 per kilogram today, but quoted prices to reach the lunar surface are from $400,000 to $1.3 million per kilogram right now. But SpaceX is hoping to lower the cost for a Starship getting to low Earth orbit to $2 million eventually, or $10 per kilogram. So lunar landings should come down in cost dramatically. Critically, for the first time, we'll have access to materials or space resources that extend beyond just photons in low Earth orbit. Once we can mine and process materials, living sustainably in space becomes possible. If we bring a ton of mining and processing equipment, but can process that into maybe 50 or 500 tons of material and finished products, that will be a game changer. Cislune hasn't raised investor funding, has been bootstrapped off of NASA grants. Cislune's first 2021 STTR showed that beneficiated or separated regolith can result in a microwave-susceptible mixture that can produce 10-centimeter layers of durable sintered bricks and other infrastructure elements. We worked with Dr. Phil Metzger at University of Central Florida to model and conduct experiments in microwave sintering and beneficiation. Our 2022 STTR was on compaction of lunar regolith that I'll cover on the next slide. Cislune's 2023 SBIRs are on minimizing sublimation of ice during excavation by minimizing heating and limiting exposure to vacuum through tumbling. We tested sublimation during and after excavation at minus 20 degrees Celsius under a dry nitrogen atmosphere to detect any water vapor that comes off. Another SBIR was for designing a 50 to 80 meter tall truss tower used for gathering solar power at the poles. Using melted regolith to cast truss joints, as you can see in the bottom right. We worked with the University of Hawaii at Hilo Pisces group to melt regolith and test cast samples. Those phase ones wrapped up in February, and we were awarded a phase 2 for ice mining tech, working with Honeybee Robotics to develop the process and test in thermal vacuum. And Cislune's 2023 STTRs are on using rover wheels during site preparation. We're working with Dr. Phil Metzger and the Exolith Lab in their Rider test bin to test various wheels. We're also building Re-Razor, a small robotic excavator to test wheel designs for rovers, gathering geotechnical data from wheel slip measurements, and if we can compact the surface while driving using those wheels. And another STTR is on robotically placing deflector cones on lunar launch pads after landing and before launch to reduce damage to the pad. And then if that doesn't work well enough, and we're looking at venting of the underneath the landing pad to make sure that there's a kind of a flame trench for the plume that does get through to escape safely without creating an overpressure and damaging the pad. Our 2022 NASA STTR on compaction was working with Dan Britt and the Exolith Lab for creating a site preparation process and an architecture for preparing the ground using excavation and compaction to create a durable surface for pathways, berms, buildings, and landing pads, using only lunar regolith as a space resource. One possibility is that the first large lander going to the site we want to build up infrastructure at could bring an excavator that can compact the regolith underneath the lander to make the surface safe for launch and for future landings. We developed CFD of the plume surface interaction using under a CLIP scale or about 1,500 kilogram class lander as an example. We tested compacted regolith simulant using compressed air plumes in ambient pressure that matched the CFD pressure gradient expected with a CLIPS lander. With the right size fractions, the regolith can be compacted into a strong surface, not affected by plume surface impingement. Without it, the plume can damage both the landing pad at the launching rocket, as we saw in Boca Chica with the first Starship launch. And I've got a quick video showing kind of unprepared lunar regolith uncompacted, and then after that. And that's the final one that's much more compact, and you saw no real depth movement there. Okay, and then we were also competing in the NASA Break the Ice Lunar Challenge in 2023, and that was at a lunar proving ground in Lucerne Valley in the Mojave Desert. And we built this based upon the Kennedy Space Center Razor excavator, or IPEX. It was a tough 15 days in the desert, but we extracted over 3.3 tons of concrete and drove it over 54 miles, 500 meters at a time. We learned a lot about robotic excavation in an austere environment, and we're busy upgrading the excavator to compete in the finals of that competition June 10th of this year. And I think that'll be live streamed. There are another 5 teams that are also competing for the $1 million top prize or the $500,000 second prize. So here's some video of our bucket run excavating concrete. And NASA thinks that's simulates the material properties that we'll see with icy regolith in the permanently shadowed craters. And separately, we're working on an app called SimMoon that's currently on the Apple Vision Pro App Store, but we're planning to release it for the Meta Quest and other platforms, including web, at some point soon. It's written in Unity, and that should allow us to have broad cross-platform compatibility. We're planning to model ISRU, settlement building, and operations as well. So with all of these opportunities, it would be great to hear from any of you that want to about collaboration opportunities in the future. This is just a quick video showing some of the initial settings for that process, if you can see that. So it's kind of just driving around an Apollo-style lunar rover. Yeah, and then I was just going through some of all the landings that have happened on the moon, and it's been 58 years since the first landing on the moon. It was about 37 years, and you can see a big difference there between the Apollo era landers and the Chang'e 3 lander that happened in 2013, which really kicked off the modern era of lunar landings. Intuitive Machines' CLIPS mission was the United States' first soft landing in 51 years. So 1,200 tons of fuel is required for each of the 3 SpaceX lunar Starship missions under contract. That's estimated. For the demo mission and Artemis 3 and 4, refueling will be done in orbit by launching an estimated maybe 16 SpaceX Starships for each lunar lander mission. This is because of the enormous payload capacity and the requirements to bring all of the fuel needed to get from low Earth orbit all the way to the lunar surface, a surface stay, including cryogenic boil-off associated with that, and then launch and return to the non-rectilinear halo orbit that the Gateway is in to meet up with and return. Blue Origin is also doing in-space refueling for Artemis 5, working with Lockheed Martin for refueling tugs on the national team. The so-called tyranny of the rocket equation means that we can barely get 5% of a rocket's launch mass to space as payload from Earth's surface. But from the moon, it can be 50% payload because of the 6 times lower gravity and lack of atmosphere. This makes moon source propellant rapidly economical compared to Earth launched. The HLS contracts are firm fixed price, so SpaceX and Blue Origin could decide to use in-space competitively priced refueling from commercial depots. Water on the moon is about 20 cubic kilometers in volume, that's estimated. And that's just the first valuable resource. Similar steps can be used that are used to extract water could be used to separate out the materials for making iron, titanium, aluminum, silicon, and platinum group metals as well. Asteroids have been hitting the surface of the moon for billions of years, and it's always about 3 days away. There's been no subduction on the moon for the last 3 billion years. The process on Earth buries heavy elements in the mantle due to Earth's active plate tectonics. That means asteroid materials have collected on the moon's surface, including volatiles like water that collect in the cold traps in the polar permanently shadowed craters. There are also significant benefits for mining and material processing of having 1/6 gravity. The business case for lunar water for refueling HLS landers is starting in 2026, we think, for the SpaceX HLS demo mission. Once 200 tons of crew and cargo can be safely landed, the new frontier will open up for what I'm hoping is a 21st century gold rush. Tourism, building a lunar research station, IP development, sale of propellant, and building materials, and real estate should come next. Yusaka Maezawa has already contracted with SpaceX for the Dear Moon mission, with 8 artists and athletes going to the moon like Apollo 8. The next step are tourist flights to the surface. DARPA recently entered the news with interest in working on the Luna 10 project, studying a 10-year lunar architecture that aims to rapidly develop foundational technology concepts that move away from individual scientific efforts within isolated self-sufficient systems towards a series of shareable, scalable systems that interoperate. At the L6 spring meeting, I think it was last week at Johns Hopkins University Applied Physics Laboratory, DARPA shared some initial results with the community, as shown in this slide, showing initial stages of lunar development. And they also had further slides showing the next steps beyond that. They also started the Logic Consortium to develop standards for lunar systems. The moon is a vast resource that is becoming increasingly accessible due to technological advancements. We're witnessing a rapid evolution in technology, regulations, infrastructure that's making lunar commercialization not just possible, but increasingly worthy of investment. The steps we take today are shaping the future of lunar commercialization and space exploration. Yeah, and thank you for attending the webinar, and please reach out if you'd like to collaborate, and I'm available for any questions.
Awesome. Thanks so much, Eric. Great presentation. Good overview of all the stuff going on there. So again, for those attendees, there's the Q&A function at the bottom. Please enter your questions there, and I'll read them out while we wait for a few to come in. I have a question or two. So you have a lot going on. You listed 7 SBIRs. What are you most excited for Cislune that you guys are working on?
Yeah, the news about 1 week ago where we got our first phase 2 SBIR is very exciting. It's a 2-year period of performance rather than the 6 months or 13 months that happens with phase 1 SBIRs and STTRs respectively. It's also more funding, and we're working with Honeybee Robotics, which is just up the road from me here, and Dr. Phil Metzger on doing a lot of good research into mining of water ice, which I personally think is one of the most immediate opportunities for refueling the human landing systems, landers, and reducing the number of refuelings that are required in low Earth orbit and beyond. So that's definitely exciting, and a lot of the construction work as well. I think will be very important for making landing pads that are safe for reusability and going back to the same sites, and kind of building up infrastructure from there.
Nice. Excellent. So let's see. So we got a question from the audience here. What was your experience like with YC and your previous company?
Yeah, yeah. So that was Tesseract, and I'd been working at Maston Space Systems in operations, um, and that was a great experience working on those reusable small vertical takeoff and landing rockets, doing some really interesting work for NASA flight opportunities. But we had an idea for kind of hypergolic propellants and things like that, and applied to Y Combinator. We're able to get in. I think they invested $125,000, and then we um, raised about $2.3 million total. So it was a interesting experience learning about the investment side of opportunities for a small business, and getting actual hardware flown in space that we were designing and building was really exciting. Um, yeah, it was a great experience. It's definitely a very different path, and Cislune may do fundraising in the future, but um, it's been really interesting to kind of talk to NASA and be closer to what the customer wants, going to conferences like Earth and Space and the LSIC meetings. Um, so it's just yeah, exploring a different path with this company. But yeah, interesting both sides.
Excellent. Yeah, definitely exciting journey. Good lessons learned throughout those. So another question here. What are your plans on finding the best or a good place for water ice mining slash prospecting?
Yeah, it is a prospecting is critical, and um, I know there's the initial work with the Trident drills. I think two of those missions will be doing some initial prospecting, but I think we're going to need significant um, remote or from orbital observations at higher detail. Lunar Trailblazer should help with that to some extent. Um, but then actually getting into the craters, into the maybe 50 Kelvin temperatures, and starting to test equipment, being able to traverse in and out of those craters, it's going to be um, challenging but exciting opportunity for technology development and prospecting. But it does seem like that's one of the most immediate opportunities economically on the lunar surface. So I think that's critical. NASA's going to do its part, but I think at some point soon, commercial companies will have to be able to do the prospecting and start to find reserves and raise the funding to be able to actually exploit those.
Nice. You started to answer one of the questions I had, maybe just kind of continuing on that last point of the role you see that NASA starts to play in the future versus commercial
Right.
companies.
Yeah, and I mean, I think it was exciting as well that DARPA and the Department of Defense, by association, are starting to dip their toe a little bit into lunar surface. I know that there's some concerns about the Outer Space Treaty, um, not wanting to have uniformed military on the surface, is I think their understanding. So potentially quite a bit of funding from government sources, but I do think the uh, commercial companies, like Lunar Outpost, for instance, um, will be critical for actually growing this and making it into something beyond what we have with research stations in Antarctica, which are great. But I think the commercial opportunity and the potential of space resources can really grow if we can get commercial companies and the investment that comes with those to start developing and growing that opportunity and proving it out, so investors can add more money to the equation than someone like NASA can. So I think NASA is likely to be hopefully an anchor tenant, but then being able to grow from there is critical so we don't just rely upon the politics and everything else of budgets.
Yeah, for sure. Let's see, we got another question coming in here. So you mentioned hydrogen peroxide as a non-cryogenic fluid useful in fuel cells. Can you elaborate a little on the H2O2 manufacture? And have you looked at it in combustion as well as fuel cells?
Yeah, yeah. So it is something that we're actually looking at putting in a grant application for and looking into that entire cycle. I know one of the challenges, for instance, with liquid hydrogen for fueling cars and trucks is that some of the efficiency of each of those transitions, liquefaction, green hydrogen versus gray hydrogen, those kind of things, so far have led to lithium ion battery being a more successful commercial venture. So that's kind of the next step there. I know that Rice University and Orbit Fab have some kind of licensing arrangement to do direct synthesis of water into hydrogen peroxide using catalyst and electricity. So yeah, it's low TRL. It's something that I'm excited about. I know the hydrogen peroxide fuel cells are also things that are currently in academic settings, but it does seem like a significant opportunity to have a room temperature storable that doesn't require liquefaction, zero boil off technologies and cooling to extremely low temperatures, the challenges of hydrogen embrittlement. And the reason I brought that up was my previous company was kind of along the same lines of interest, where hydrogen peroxide is a ISRU-able propellant as well. So you can run it back through a fuel cell and generate heat and electricity, but you can also just run it through a cat bed of platinum or silver generally and create thrust. And it's about 170 seconds of specific impulse as a monopropellant. But using the extra hydrogen that you get through the direct synthesis process and just compressing it as a gas, you can store that in COPVs and things like that at 8,000 to 10,000 psi. And you can get about 340 seconds of specific impulse, which, although it's not quite as high as Hydrolux or liquid hydrogen and liquid oxygen, I think it's maybe the math works out where that's competitive because it doesn't require zero boil off, extensive cooling, liquefaction, some of those challenges. So it's something we're looking into.
Nice. A lot of challenges,
Yeah,
but they're fun challenges.
I think so.
Nice. So another question here. I think this is referring to a point you made in a previous question or two. So going in the other direction, do you think that commercial resource extraction on the moon will have implications for resource extraction in Antarctica?
Interesting. Yeah, I mean, I think although I'd love it if there was more, if it was more economical to have more people there, I do think the mix of robots to people that can service them and keep them running is going to, maybe it's 10 to 1 or 20 to 1 or 50 to 1. So I think that that's how you can make this economical is humans are brilliant and very dexterous, so they can repair the robots is kind of the architecture that I have in mind. But I think fully robotic is going to be very challenging for a large resource extraction process. So I think there will be some people in the garage that are repairing the robots and then sending them out to do the work. So I think that same technology is going to create spin-offs that do affect Antarctica, and that is something that we've looked at a little bit with Stanford and some of the scientists in Antarctica. They drive these large vehicles all the way from McMurdo to the base at the center of Antarctica, and that requires it's a risky, bit dangerous endeavor. So if we could automate that, I think it could allow more frequent resupply even during the winter months, and more frequent during the summer. So anyway, it's I think robotics is going to technologies are going to definitely affect both of them.
Nice, for sure. So you've, touched on a couple different challenges and the resource extraction and excavation, as well as, some of the policy considerations and legal. In achieving that vision that Cislune has that you outlined at the beginning, what do you see as some of the biggest challenges to achieving that?
Yeah, I think I mean, the critical thing I think that's affected even low Earth orbit, which is slowly getting solved, is just the cost, of course. At even $2,000 per kilogram, it's very challenging for anyone but millionaires or billionaires to afford going there and even doing the experiments. I think that is getting solved slowly. And the benefits that happen in low Earth orbit, there's kind of a gearing effect for reaching the lunar surface. And so it will be more expensive. It just requires more energy to get to the lunar surface, and it's more complex. But all of those changes, and as soon as SpaceX Starship is able to reach low Earth orbit and come back in a fully reusable state, that'll also hopefully drive down costs significantly. And hopefully some competition for SpaceX will also cause more of a price reduction in getting to space. That's really the key. I think the old Heinlein quote about, if you get to low Earth orbit, you're halfway to anywhere, is part of that. So it's just critical for us to get that toe in the water and then be able to go from there. And I think the costs are dropping quite significantly, but we have a long way to go. Of course, getting back to the moon, even the missions for Japan and the U.S. recently were, they soft landed, but there was some damage to the vehicles, and I think they will fix those very quickly, and then hopefully we can go from there.
Nice. Yeah. Keep those questions coming from the audience. But yeah, that's so I guess sort of in summary, you think Starship or and more broadly cheaper access is the biggest enabler to opening up the cislunar economy.
Yeah, yeah, and I think the money that NASA is investing into the Artemis program is very significant. It's I think that may have been partially driven by China, as well as technological developments, lowering the cost of access significantly, as well as uh, excitement about not being, not just leaving it to China and India and the other countries that were coming online with lunar landings. So it's an exciting time as the world seems to be heading back, and with robotic technology and lowering of the cost, I think there's a real opportunity for sustainable lunar surface access enabled by space resources.
Yeah, absolutely. Let's see. I I have more questions, but let's get some from the audience. I'll give you guys 1 minute.
Yeah. So next for Cislune is the Break the Ice Lunar Challenge Finals. That's in Huntsville, Alabama on June 10th through the 13th, I believe, or 12th. So yeah, we'll be leaving Los Angeles and heading out there with our excavator, and it's just 1 hour of excavation and 1 hour of driving. That's on a kind of a lunar proving ground against the 5 other teams. So that's kind of the next thing, and that'll be webcast by NASA.
Nice. It'll be gravity offloaded too, is that right?
That's right. Yeah. For the excavation portion, they'll be weighing the empty excavator and offloading 5/6 of that with a kind of a truck crane. And yeah, so that'll be challenging during the 1 hour of excavation. So we just yesterday bought a gantry crane for our shop to be able to simulate those gravity offloads. and excavation and be able to test that more extensively in preparation.
Nice. Yeah, that'll be quite challenging. I'm excited to see, yeah, that webcast of just gravity offload sort of realistic scenario at this scale.
Right.
That'd be good.
Yeah, the transit portion is 300 meters over, they'll have simulated craters and other things to work around rocks and boulder fields and things like that.
Nice. All right, we got two questions that have just come in. So have you looked at walkers versus rovers for crater prospecting?
I haven't too much. Yeah, it is always interesting as a possibility. I was at, I think it was yeah, it was at the LSIC conference last week. They had one of um what is it called? The Boston Dynamics spot kind of four-legged things walking around. So that was pretty amazing and interesting. So um yeah, I think that's part of what's exciting about this is that everything is going to get tested, and as much as you try to do vacuum testing and thermal vacuum and everything else, it's the lunar surface itself is going to be interesting to actually test on and try to get durability and survive the lunar night.
Yeah, absolutely. I think there's only testing is key, but there's only so much you can do. We just got to get there, and I think we're just going to learn a lot about it once we're there. All right, another question here. Are there any other space companies you would like to start in the future?
Yeah, I mean, my career is really, yeah, I was, yeah, one of the first things was building that amateur built airplane, and that was exciting, trying out a Corvette engine as a powertrain for that and building it over a couple of years. That was great, but didn't feel like there was as much innovation possible with airplanes. I know it's starting to happen with electric, um, but there is a lot of regulation. Whereas I think for space, I thought the first thing that was needed was lunar landers. Was able to kind of scratch that itch with Maston. I think, and shortly after I left, they got their CLIPS contract. They were recently bought by Astrobotic. But yeah, there's a number of companies that are enabling surface access, and I think the big HLS scale ones are the ones that will hopefully drive the cost down quite dramatically for that. And so I think that's being addressed as far as transit. But then I wanted to look into the kind of next steps in the chain. I thought propulsion to get to the moon was needed from low Earth orbit, so that's why we worked on Tesseract with hydrogen peroxide, which is a nice ISRU-able space resource that you can get from water. And then with Cislune, we're looking at various technical challenges through the NASA SBIR and STTR programs to try to just knock down as many of the technical dominoes that need to be that are kind of blocking us right now. And I know, yeah, I think NASA had identified 180 or something shortfalls that they want feedback on. So there's a lot of challenges, but I think they're all there's nothing that breaks physics. We can do this, but being able to do it sustainably and profitably is the next thing that we need to do.
That's right. I think there's always a good the Space Resources Roundtable.
Yeah.
I forget who first asked it, but they ask it every year of how many MBAs are in the audience, and it's generally basically none.
Yeah.
Said until we get a large group of MBAs in here, this isn't going to happen because that profitability piece is the business side of this is really tough.
Yeah, I mean, they do have a decent number, a few people from the mining industry, which I think is really critical. The kind of budgets that a terrestrial mine charges, it's billions of dollars potentially. So it's in the realm of what we're looking at. So that's a start. But yeah, I think as business becomes more real, we'll have more investment and more investors and MBA types as well.
Yeah. All right, another question here. Other than water, what do you think will be the next ISRU resource?
Yeah. yeah, I've been talking to people about that, and I mean, one of the interesting ones I had dismissed it previously, but is helium-3. It is a bit of a challenge, of course, for if it's just for fusion, but it's also useful for um, radi radiation detection, things like that, and as well as in the medical industry. So that's possibly something that can actually justify kind of export from the moon all the way to the Earth's surface if we can figure out a lot of technologies along the way, as well as generate more demand um, from a fusion process that's starting to close and actually requires it. So yeah, it's tough to have something that's actually an Earth export, but I think then uh, things like making metals on the moon is one of the very interesting things I know NASA is looking at, as well as um, DARPA with some of their funding for Luna 10, looking at like with Northrop Grumman making a railroad, for instance, will require a significant amount of metal, but you get very low rolling resistance by having those rails, and aren't disturbing the regolith so much. So maybe that's a solution. So yeah, it's going to be interesting, and there will be a lot of commercial challenges in getting that up and going. But hopefully, with some government funding, we can then go into the commercial side and start to develop the business.
Absolutely. Let's see, we've gone through the queue. I'll give it another 30 seconds or so to see if any additional questions come in. But just while we wait, any sort of final remarks from you, Eric?
Yeah, it's an exciting time. Yeah, we applied, and I think one of the key things for our success so far has been collaborating with great people. University of Central Florida with Phil and Dan and their teams, Pisces in Hawaii. It's been really interesting to meet the community. It's things like Space Resources Roundtable, Earth and Space Conference, LSIC. It's really an exciting time to be looking at lunar technology. So yeah, glad to be involved, and please follow up. I'm just Erik at cislune.com if you want to reach out after this call.
Awesome. Well, I think that's all our questions then. So we'll wrap it up a little early.
Yeah.
Thanks everyone for joining. Thank you very much, Eric, for the talk and answering all the questions. Again, we do this webinar series every month, so stay tuned. Again, typically near the end of the month, we'll have a new guest in May. So thanks everyone.
Thank you. Bye-bye.
Bye.